Min terms and max terms. Truth tables help determine the input combination that will yield a certain output value. This is useful when we want to translate a given truth table into a Boolean equation that can be much easily manipulated and simplified before actually building a circuit. There are two complementary terms that we use to accomplish this, the min terms and the max terms. Min term represent each row of the truth table that has an output of 1. To translate a truth table row into the corresponding min term, we AND or multiply each of the terms at the input inverting, applying NOT operation to each variable whose state for that particular row happens to be 0. In this slide, we can see a truth table, and then all the rows marked with an arrow represent the midterms of the table. The equation for this table will be z equal to a taste times b times c taste plus a times b taste times c taste plus a plus b plus c. Min terms are also called the sum of products representation because of the way they are end up arranged in the equation. Max terms, the other terms to accomplish the translation of the tables. Complementary operations of the min terms, obtaining for the rows that have 0 in the term as the output. In this slide, we can see that the zeros are the max terms. The rows that have the 0 in them has an output. The equation for this one will be z is equal to a plus b plus c times a plus b plus c taste times a plus b taste plus c taste times a taste must b must c times a taste must be taste must c plus c. As you can see, instead of multiply each row in the parentheses, they add the letters. That means there are the rows. And here, instead of sum each parenthesis, they multiply. The max term representation is also called a product of sums because the way they are arranged, how I was telling you, they are arranged in such a way because if any of term is 0, then the opposite.
Karnaugh maps. Karnaugh maps are a method used to simplify Boolean expressions without using algebra. The Boolean expression must be in sum or products format before they can be put into a map. Remind you what sum of products was. Remember, sum of products we talked about back is something that ended together, or the sum of the something else over together, or the something else ended together. It has this, or this, or this.
Mr. Diaz, and we talk about maps. And we exercise with 2, 3, and 4 variables. Now I'm going to start with 2 variables, which are A and B. In this case, we have A right here and B right here. In this case, we apply 0, 1 and 0, 1 for both. But we got 0 and 0, 0, 1, 1, 0, and 1, 1. It goes first A. Letter A and then letter B. This we can convert this to a different chain. Notice we write a NOT letter in the case we have 0. So now we're going to continue with 3 variables, and 3 variables that are a little tricky. Zero, 1, because we're taking 0, 1, 0, 1, 1, and then 1, 0. We can convert to the same thing as we do it with 2 variables.
Hello, my name is Roberto Alanis, and I am going to talk about how to reduce logic functions using Boolean algebra. Boolean algebra has its most usage reducing logic functions, as I said. That means if we want to translate the logic function into a Boolean algebra one, we must use some algebra rules that will help us to reduce the logic function. As a consequence, we're gonna get less components, but the result will work as it did it. Actually, some companies see this as an advantage because they use less components. Okay, now let's see the three most important Boolean algebra rules that we have to reduce logic function. Well, the first law is called the commutative law, which it will be A plus B equal to B plus A. Well, the second law is called the associative law, and it works as A plus, we open parentheses, B plus C, we close parentheses, equals to, we open parentheses, A plus B, we close parentheses, plus C. This could be also used in multiplication, which will be the same, almost the same. It could be A, we open parentheses, B by C, with close parentheses, equal to, we open parentheses, A by B, with close parentheses, C. The third law is called the distributive law. It is also called the factoring law, and an example could be A, we open parentheses, B plus C, we close parentheses, and it will be, well, the equal will be A by B plus A by C. Now let's see an example of logic function simplification. For example, could be
A plus B, we close parentheses, by A plus C. Well, the result will be first that we have to multiply A by this and by this, and the same with B by this and by C. Notable products that it will give us A by A plus A C plus A B plus B C. Now, as the fifth rule says, A plus AA will give us the equal of A plus AC plus AB plus BC. Now we have to find a like term and pull it out. That will be A. There is an A and an A, an AC and AB. You have to make sure you leave the BC alone at the end, making this, which will be another rule. I'm sorry for the mess. Which will be 1 plus C plus B plus BC. That says that any D with 1 is a 1. We almost finished, and the rule will say that any D unread with 1 is itself. That means that A plus 1 plus BC. Finally, it will give us as a result A plus B. Let's see. This will be our result. This is how reduce a logic function using Boolean algebra, following the the Boolean rules. Now let's analyze another example. For example, we open parentheses, the night A plus B, close parentheses, by A plus B. Well, we have to find AB and put it out. That it means that we're gonna get B, we open parentheses, the night A plus A. Now here says that anything read with its own complements equals 1. That's why the B. Giving us that anything ended with 1 is itself. This means that if we have two A's, it's gonna turn to 1, giving us the result of B.
Hi, my name is Erika Rosales, and I'm going to explain you the Boolean algebra operations. The Boolean algebra is the mathematics of digital systems. It helps us to structure logical thought and represent digital circuits with its inputs and outputs. We have three main types of Boolean expressions that are based in binary constants, binary variables, in basic logical operation symbols. In the Boolean expressions, we're going to find three elements. That is going to be the variable, that could be 1 or 0 because it's based in the binary system. We're going to have the inverse, that is going to be the opposite of our variable, and the literal, that it's going to be the complement of our variable. In the image, we can appreciate that we have also the inverse of the main logic gates, or related with Boolean algebra, that is going to be the AND or a NOT gate. First, we're going to start with the NOT operation function. The NOT operation, also known as inverse or complement operation, is going to change our value to its opposite digit or variable. For example, in this case, we have that to represent the inverse of a variable usually appears an overbar in the variable, or sometimes it appears as prime, as in this case. Every function is going to have its truth table, that is going to show us the combinations that we can do, and its symbol. For example, here, as I said, in the NOT operation, we're going to have the opposite of our main value. For example, in the truth table, we have our variable a, and we have 0 and 1. So the opposite of 0, it's going to be the number 1, and the opposite of 1, it's going to be the number 0. And in this case, our inverter symbol is going to be formed by a triangle, and the bubble, for the circle that appears after the element, indicates that it's an inverse operation. Then we have the AND operation, that in Boolean algebra it's equal to the Boolean multiplication. Here we're going to consider two variables that are going to be a and b. In this truth table, we're going to compare the values that a and b have. In this case, we're going to solve the truth table as normal algebra. For example, 0 times 0, it's gonna be 0. 0 times 1, it's gonna be 0. 1 times 0, it's gonna be 0, and 1 times 1, it's gonna be 1. So only when we have two high values in our inputs, we're going to obtain an output value. If we have two different types of inputs, our output is going to be of a low value. Then we have our schematic symbol, where the AND operation is going to be represented like a huge D with its inputs, outputs, and in the right part we're going to find how to represent these operations in using switches. If we have a 0, it's going to mean that our switch is going to be open, and if we have number 1, it's going to mean that our switch is closed. Every function, every logic gate is going to have its inverse. In this case, the inverse of AND it's going to be NAND and AND. Here we have its truth table, and it's going to occur the opposite in the operations. For example, here 0 times 0 in the normal AND we know that it's 0, but here it's the opposite, so 0 times 0 is gonna be 1. 0 times 1 also gonna be 1. 0 times 1 is gonna be 1, and 1 times 1 is gonna be 0. So in this case, two high inputs are going to generate a lower output, and different inputs are going to generate a high output. Then we have the OR operation, that in Boolean algebra it's going to be the Boolean addition. Here also we're going to consider just two variables that are going to be A and B. Here is the same as normal algebra, as I said, with the AND operation. In our truth table, we're going to have that 0 plus 0, it's gonna be 0. 0 plus 1, it's gonna be 1. 0 plus 1, it's gonna be 1. And 1 times 1, it's gonna be 1. Then we're going to explain the schematic symbol, that in this case also has two inputs, one output, but here the shape of the operation changes. It is like more longer, more extended in comparison with the AND operation. And on the right side we have how we can represent the truth table using switches. When we have when we have two low inputs, that means 0, we have 0 in A and 0 in B, both switches are going to be open. If we have 0 in A and 1 in B, the switch B is going to be closed and the switch A is going to be open. And otherwise, A is going to be closed and B is going to be open. And when the two switches have a high input, the output is going to be also high, so both are going to be closed. Then we have the inverse OR function, its name is NOR, N-O-R. The expression that indicates the inverse OR function, it's the one that appears on the left side, that it's A plus B, between parentheses, prime. Yeah, as I set prime is going to indicate the opposite, the inverse of the values that we already have. In the last truth table result, we can see that the values are completely changed. For example, here we have 0, 1, 1, 1 according to the combinations that we have, and then in the other table the switches are the outputs changes its value into the opposite values. And to end this presentation, I'm going to explain just the Boolean operations properties. We have two, the cumulative and the associative. The cumulative, we can find it in additions and multiplication. Addition with the OR gate and multiplication with the AND gate. In addition, it means that it doesn't matter how we order the factors that appear in the addition, the result is always going to be the same. In the multiplication, is the same as the addition. The order of the factors are not going to interfere with our outputs. And in the bottom of the slide, we can find how these properties are represented with digital circuits. In the first case, we have the VR, that means a sum between B plus C, and then at the end we have the AND, that is going to indicate a multiplication between A and B plus C, and that is the expression that is represented in the upper of that image, that we have A times B plus C, it's equal to A times B plus A times C. And in that case, we find that, yeah, the order of the factors don't interfere in our result, but the digital circuit changes its diagram. And at the end, we have the associative property. In additions, it's gonna mean that we can divide our factors in different groups while they are in a addition. In that case, we won't alter the result, the final result. And after the first expression, we can see the schematic symbols where in the both images we see that where they are applying the OR operation because we are making additions. So in that case, the order of how we put our variables or factors are not going to interfere in our results. The multiplication is the same explanation, and yeah, it's kind of the same. Well, they are just multiplying. The section we made won't interfere, won't affect our output results. Yeah, just the sequence of the digital circuit may change, but the result is gonna be the same. So that's all from my part. Thank you.
My name is Jose Emmanuel. I'm going to talk about ICs before talk about decoders and multiplexers and all stuff. We have to remind that ICs are most of all are made of silicon, and silicon is the base for all electronic devices.
The digital integrated circuits technology has advanced rapidly from the use of the single transistor in these forms is the basic unit for the next families. With all these in the market we can find all these kinds of designs of package which are specified by its number and the way that their pins are connected. And the small scale integrations means that all our circuits and our gates we will find in a number between between 2 or less than 12 gates per chip. And then with a medium scale integration means that the gates inside the circuit goes from 13 to 99 gates per chip. And then we have a long, which means that the gates inside this package goes from the range of hundreds of gates. 100 of gates only in these kind of circuits. And then from medium we have the large, and the large then we have the very large, which means that inside instead of hundreds we will find thousands of gates. Can you imagine that? It's a lot. But guess what? We have more, ultra large. So it means that we are not talking about thousands, we are talking about hundreds of thousands of gates. So it's incredible how the technology has advanced, because nowadays we can find giga. Giga numbers means that are more than millions gates. When we explain Boolean algebra and single gates, we make some operations about 2, 3, 4 AND or XOR gates. But when we're talking about giga, it means that has millions and millions of gates, and the algebra implied means a complex calculus of that.
Hello, I'm Gustavo Ortega, and I'm going to talk about the multiplexers. A multiplexer is a combination of circuit with 2 to the n input data lines. The input sections line determine which input data is going to be selected to the output. It may also have an enable input. The enable input needs to be activated to make the multiplexer works. If you don't have the enable input activated, it doesn't matter what you do with the multiplexer, it won't do anything. Here we have a draw of a multiplexer. A multiplexer is a digital switch that has multiple inputs and a single output. The select lines determine which input is connected to the output. Here we have the inputs and the output. The inputs can vary depending on how many data you need to pass into the line, to the output. It depends on how many lines of input you have, and how many select lines you will have. If you have 2 input lines, you will have 1 select line. If you have 4 input lines, you will have 2 select lines, and so on. Here we have an example. We have the 4 inputs, D1 to D3, D0 to D3, sorry. And we have the selective lines that are A and B. And we have the output that is the letter Y. It depends on what do you have in the selective lines, what you will have in the output line. If you have 0, 0, you will have D0 in the output. If you have 0, 1, you will have D1. If you have 1, 0, you will have D2. And if you have 1, 1, you will have D3 in the output. Then we have a draw of a demultiplexer. It's the same but backwards, because you only have one input and you can vary on the output you have, but you also have the selective lines. For example, if you have 0 in the input, it doesn't matter what you have in the selective lines, you will have 0 in everything. Then if you have a 1 in the input line and you have 0, 0 in the selective, you will have the input in the Y0. If you have 0, 1, you will have the input in the Y1. If you have 1, 0, you will have the input in the Y2. And if you have 1, 1, you will have the input in the Y3. The demultiplexer is a digital function that performs inverse of the multiplexing operation. It has the one input line, E, and it transmits it to one of the two to the n possible output lines, D1 to D3, D0 to D3. The selection of the specific outputs is controlled by the bit combination of the n select inputs of the lines of selection. And here we have the draw of the multiplexer. It's the same, but we have just one input and the outputs vary. You can have 2 outputs, 4 outputs, 8 outputs, and 16 outputs, or any number from 2 to the n number of outputs. And it also depends on how many outputs you have in the multiplexer. It's the number of select lines that you will have in the circuit.
To summarize, we have finally the decoders and encoders. These two final function blocks are basically another name to name multiplexer and demultiplexer. Why is this? Because it has the same function as we said before, as we explained before. But that means allows to systems to send information to just one wire, and then all the information translated into the through the multiplexer and sending back to the computer to be processed. This allows systems be more safer, because the information just travels through just one wire, and then you have to select for which channel you're using for the multiplexer. This allows systems to be more complex and easy to choose and handle. And also we have the encoders as a function as the multiplexer. Their function is to take all characters incoming or input incoming or data inputs, and then the result for different inputs is just one input both, but with all the information through just one wire. And this allows to through the selected lines be possible to show all that information in just one wire.